Say hello. Good morning, everyone.
Good morning.
So yesterday, in the last class, we study about the maximum likelihood estimator and the maximum a posteriori estimator. So what is the main difference between these two estimator? The main difference is this, that the maximum likelihood estimator uh, do not know the p of x. So in this case, the p of x is unknown, so we cannot use the Bayes theorem. So Bayes theorem is used to find the a posteriori PDF, but this estimator do not know the priori PDF p of x, so it just know the uh, this variable x and z. Okay, so it's just know the true value of x, that is x naught. So this is the main difference, and the MAP estimator know the priori information about the p of x, so it used Bayes theorem to find a posteriori PDF. So this is the main difference, and the maximum likelihood estimator apply the maximum uh, likelihood. Okay, maximum likelihood of x, this equals to z. Okay, and this is the formula for likelihood. Likelihood is denoted by PDF of z condition on x. Okay, so if there is observation knows about the x, and x is, in this case, is a non-random parameter. This x is a non-random parameter, but this x is a random parameter because it was calculated using this measurement, and this z is non-random. Okay, so the x unknown constant is a random parameter. So maximum likelihood estimator used for the random parameter x, non-random parameter, it used for non-random parameter. X is a non-random parameter and constant, but z is a any random variable observation from the sensor output. So the estimator is find the this value using the z. Okay, using the observation, there is a single measurement. This single measurement which is coming from the sensor is a non-random. This single measurement is a random variable, random observation. So this XML is the random. Okay, so this equals to this likelihood. This is just notation for the likelihood. Likelihood is equals to this one, means it find the likelihood of the z conditioning of x. What is the likelihood of this measurement, that this is the x? Okay, what is the likelihood of this z, that it is originating from the this constant value. Okay, and having a Gaussian variable which have a mean x and the variance this one, and this equals to this one. And then if you know about the p of x with mean and the variance, then you can apply the Bayes theorem. And now this is known as a MAP estimator. So MAP estimator knows about period information about the parameter, is that x is given with the mean and the variance. Okay, so and so we can apply this thing. So this is the main difference. Okay, so the MAP the likelihood estimator is equals to the z, likelihood of the z, and the MAP estimator is equals to epsilon of the z, where epsilon is a function of this thing. Okay, if we solve about the this part, if we solve about this part, okay, then this will come. Now when map will coincide with the maximum likelihood estimator, there is some certain period PDF when map is equals to the ML. This is called the diffuse PDF. Now, this diffuse PDF is a certain PDF when map is equals to the ML. Both are same. So this is called the diffuse PDF. Okay, and how this can be seen by rewriting the denominator in the Bayes formula. So you know the Bayes formula, the denominator is the total probability theorem. The integral from minus infinity to infinity, it will it is the product of the sum of product of the this numerator part. Okay, so assume that p of x is known over a region having a length 1 upon epsilon. Okay, so suppose p of x period information is known over a region, so we can replace p of x with the epsilon. P of x with the epsilon. The epsilon is nothing, is any constant value, and in the constant, and there is some region that this region is x. This region is x, and the name of the region is epsilon. Okay, and epsilon is greater than 0 but small. So here we can say that for x less than 1 upon 2 into epsilon. So now we can put the value of epsilon here and here. We just replace p of x with epsilon. So if we put epsilon in p of z, then this will come epsilon g of z. G is just replacing this variable. This total probability theorem is just used for normalization. Okay, the denominator of the Bayes theorem is used for the normalization of the Bayes equation, which must equals to your unity. So we just replace with the g. G is used for generalized normalization constant. Okay, so g of z. Okay, now put this thing in the Bayes formula. So in the Bayes formula, p of x is replaced by epsilon, and p of z is replaced by this thing here. Now epsilon cancel. Remaining part is this one. Now g of z is nothing but 1 upon c. It's a constant like this. D 1 upon c constant, as we already replaced this 1 upon c instead of p of z. So this is the same value, the 2 pi variance and variance not. Okay, variance not is for the true value and the variance for the periodic PDF. So c equals to 2 pi variance and variance of not and p of z. Okay, so now final question is this one. So you can see that this is value is constant and p of z is the likelihood. The same is the same answer of the maximum likelihood estimator. So your maximum likelihood estimator is equal to the likelihood. This is your likelihood estimator is equal to this one. So your likelihood estimator equals to this one, p of z, and p of z equals to, when we solve, is equals to z. Means the map will coincide will meet the maximum likelihood estimator using the diffuse pdf like this. So here we convert map to the maximum likelihood estimator with having some constant. So this diffuse pdf is improper pdf because as epsilon tends to 0, it does not integrate to unity as proper pdf. So in the Bayes formula, the p of z becomes when integrates, it becomes a unity, so that is proper pdf. But in this case, as epsilon tends to 0, then it does not integrate to unity as the previous one, as a proper pdf. So this is called the improper pdf. So another name for the diffuse pdf, that it is non-informative pdf because it carries no information. Because we replace p of x z over certain region epsilon, but where is x? We don't know. This is some region epsilon, but where is x? We don't know. We do not know. Here is x, or here x, or here x. Where is x? So x is still informative and non-informative. We just replace the over a certain region epsilon, but it carries no information. So no information about the parameter. Where is the x parameter? So uniform distribution over an infinite interval at the limit. So it just show you the diffuse pdf to differentiate what is the main difference between these two estimator, and when we can use such type of estimator. We can use both estimator like this one, and we can use separately like a maximum likelihood estimator and the other thing map estimator, and we can use both estimator together for the non-Bayesian and the Bayesian cases. So a diffuse periodic causes the posterior pdf of x to be proportional to its likelihood function. When we use this diffuse periodic pdf, this causes the posterior pdf of x to be proportional to the likelihood like this. This is now the posterior pdf is proportional to the likelihood, and thus map estimate to coincide with the MLE. So the non-Bayesian MLE is, in view of above discussion, nothing but the Bayesian map. MLE is nothing in above discussion, but it's a map estimate with complete period ignorance. We just ignore the p of x. Otherwise, the MLE is same as a map estimator. So this thing is reflected by the diffuse period. So if we want that MLE becomes same as this one, then it will use the diffuse period. So that both can be used. Clear? Now the sufficient statistic and the likelihood equation. So sufficient statistic is g of z. Okay, as we have already seen that we replace the epsilon, rather than considering all the measurement, why not we just use a small part of the region like x or like epsilon. Okay, this will save your time. So epsilon is nothing but a small region of the whole surveillance region. So what is sufficient statistic for the estimator? So sufficient statistics is can be obtained by when we decompose the likelihood estimator by f1 and f2. So f1 includes g of z, and g of z is a total probability theorem. For the small part, we just decompose. Okay, make a partition of the z. We have partitioned the z, which is a complete set of the data. So then it is clear that the maximum likelihood estimate of x depends only on the function of g of z. So g of z is called sufficient statistic because we assume that our periodic information lie in epsilon region, or so we apply the g of z as a total probability theorem, or to normalize the equation. So the g of z is our sufficient statistic rather than this part. So we just decompose we just decompose this equation with this one, and where g of z is a sufficient statistic. So rather than using the entire data set as z, so it summarizes the information about the x content in the entire data. So it summarizes the information about the x, that x is contained in g of z. Okay. So this is example. Consider the scalar measurement. So where j is 1, 2, 3 up to k, and similarly x is constant value and omega is j. So there are j measurements for the constant value, for the unknown constant variable x. So these noise components are independent and identically distributed, zero mean, Gaussian random with variance, this one. So if this is the Gaussian, then g of z is also Gaussian with the mean and variance. Thus the likelihood function of x in terms of zk, this thing. So we have to find the likelihood of the x in terms of this one. So this is the observation, and this observation is used for measuring the likelihood of the x. What is the likelihood of the x? That it is belonging to this measurement. So again the equation is same, but here zk, previously the single measurement, now there are many measurements, so we can replace this part like this one, p of z1 comma z, p of z2, and up to z of k, and conditional of x. This is same thing, but here the many measurements, so we just expand the set z like here, and then we solve this thing, and this is a Gaussian variable. P of z is a Gaussian variable, so it is equals to this thing. Now the likelihood function above can be rewritten into the product of two functions as in 19, like this one. So it can be rewritten as a two terms like this one. Here we just expand the square, this part, okay, this is a square, this is a solution of a square, and then we just separate epsilon and this part and epsilon of this part, and taking in common, okay, because we want to make this equation similar to 19, similar to this one, because as we are partitioning, we are finding the sufficient statistic like this one. Okay, so first we solve this thing. This is a Gaussian variable, like this Gaussian variable. Now solving the square root and separate the sufficient statistic from this part, like this one. So if we solve the square root square formula and to separate the things, and so among this equation, what is the sufficient statistic? Is this one f1 g of z. This is a sufficient statistic, this part. So this part is f2 of z. This includes the z, f2 of z, and this part is equals to f1 g of z comma x. So f2 of z is this one. Now the f1 g of z is this thing. Okay, this thing. So g of z is equals to this variable. How it comes? When you solve about this one, so this you can easily find the g of z, the sufficient statistic, is equals to this equation. Okay, this is a simple algebraic calculation. Up to here it's clear. Any question?
So
This part is this one, and this part is this one. Epsilon k and x to z, because this thing is the v, and this thing is a 2z. This is the likelihood here. This thing is the likelihood z.
At the formula, the sufficient statics is same as mean.
Sufficient
Sufficient statics is same as mean.
same as
Mean average.
mean.
At the formula.
Yeah, this is the yes, it's same as the mean value. Sufficient statistic is the same as the mean value, and this is equals to this thing, and this whole part is z mean. The maximum likelihood estimate, the answer of the maximum likelihood estimator z. This is same as a maximum likelihood. Okay, so this equation is an example for the likelihood equation. So this the sufficient statistics is equals the maximum likelihood estimator. Okay, so in the maximum likelihood estimator we use the likelihood function to find the what is likelihood of the x, what is likelihood of the x based on the observation z. So it is a likelihood, it's equals to mean value of the z. So thus according to the definition 19, z is sufficient statistic for estimating the x. So this is if we come to know the z, then this is sufficient information to estimating the x variable. So now to maximize the likelihood function 22, we apply the derivative, and with respect to, we apply the derivative with respect to x and equate it to 0. So since f2 is independent of x, the likelihood of this one, we just use this one, because here there is no x, so we just did derivative with respect to the x. So we use the sufficient statistics for the likelihood, and derivative it with respect to x and equal to 0. So using the derivative of log likelihood function, such as, because logarithm is used to ignore the effect of exponential. If we apply the logarithm on both sides, then this part will come down and exponent can be ignored. So this yields the derivative of log likelihood equals to the derivative of log the sufficient statistic, because here is the x is included in this part, but f2 do not include the x, and this equals to this thing. So power of this thing is come down here, and exponent in this equation is ignored. So this is same thing, and when we solve it, it equals to the z. Okay. Here 2 to cancel this part, when it cross across the equal sign, it will be 0, then x equal to z mean. Okay, so your estimator equals to the z mean. So this is sufficient statistic to find the to estimate the value of x. Okay, clear? Any question? Here we just decompose the whole entire data set to find the sufficient statistics. So this is our decomposition when we solve about the square of the exponent, and this is the decomposition. Now we have to apply derivative with respect to x to find the likelihood of the sufficient statistic. So this is our sufficient statistic. So we apply the derivative over the function, and it will comes the mean of the z. So now let's complete the remaining part, the least square estimator and the minimum square estimator. So in the first two parts we cover this thing. So what is definition of least square and the minimum mean square estimator? The least square is used for the estimating non-random parameter. Suppose we have given this measurement set, okay, where this h is a just function, is a function of x with j values, function of x with j values, and the omega has j values. So the least square estimator of x is this thing, okay. So the least means what is the least estimation. Least square means what is the least estimation of x. So the least estimation, for the least estimation we just take the minimum of x, and in the previous lecture maximum likelihood we just take the maximum value of x. So there is difference between maximum likelihood and the the least square, although both are same, but both are opposite, but however both are same. So this is the least square which takes the minimum value of this parameter. So this parameter is equals to the g of z minus h of this thing. So this is non-linear LS problem. If the function h is linear in x, then one has a linear problem. So assume that the noise omega w of j is independent, identical, distributed, zero mean Gaussian random variable like this. Then LSE coincides with the MLE under the assumption, under this assumption. So if this is the IID, then g of z is Gaussian with mean of x, where h is the function of x, and variance. Okay. So similarly, the likelihood of the x is then this thing. So now there are many measurements. So we just expand z of k. This is the likelihood. We just expand z of k like this one, and condition of x, and which is equal to the Gaussian value of this one, because our z is Gaussian. So is equals to the z, the Gaussian value, Gaussian of z having mean and variance is equal to this thing. Now the minimum of to minimization of the 2 is equivalent to the maximization of 2 of MLE. That is the ML method is disguised ML approach. Means that this is both are same, just is it hide the importance of the maximum likelihood, but otherwise both are the same. Because when we assume that this is also the zero mean this thing, then it comes to the same answer. So and the mean square error is the minimum mean square error estimation. This estimator is used for random parameter. It typically defines the quadratic cost function. Means the quadratic cost function is the expected value of the error, expected value of the error. This is the error, the estimator minus the true value. This is the error, expected value of the error, and we take the minimum of x of error and takes the expected value of the error, conditioning of the z. So it just defines the quadratic cost function. The solution of 4 is the conditional mean of x. So the solution of 4 is the conditional mean of this thing is equals to expected value of x condition of z, and equals to the integral part of the x into p of conditional probability of x conditioning on z into the x. Okay. So where the expression is with respect to the conditional Pdf from the bias. This is from the bias formula, and x is a period. X is a variable x. The above equation follows by setting derivative of 4 with respect to the estimate x and equate it to 0. So if we apply the derivative here with respect to the x estimate and this expected value, because here is equal to expected value, condition of z, when we solve about this thing, this will equal to this one. This is the derivative of this thing. Okay, this is derivative of this thing, and this when we solve, because 2 is a constant, and when we solve, this will equal to this thing. Okay, so that's the expected value of x, condition of z, and this estimator is same. The MMSE estimation problem is a particular case for Bayesian estimation where the expected value of a positive definite cost function is to be minimized. With the help of this thing, we minimize the expected value of the error. There are some LS estimator for a single measurement and for a several measurement. For a single measurement problem for an unknown parameter x, like this, the least square criteria leads to this one. The same formula, minimum of x, z minus x equals to z, which is the same result as estimator if omega is 0 mean quotient. So how this come? There is the same thing when we solve this equal to x. How? We apply the derivative. We apply the derivative as we did in previous equation. Like this, when we apply the derivative, okay, when we apply, because both are same, and the maximum likelihood we apply the derivative, okay. So here when we talk about the maximum likelihood estimator, where there was a argument maximum x, we apply derivative. Here when we apply derivative, then to here, this will equal to 2 of z minus x, and equate this equation to 0. Then when we move to 2 across the equal side, it is 0, and then x equals to the z. So which is the same result as the maximum likelihood estimator if we consider the omega is 0. So this is due to the fact that maximizing the likelihood function, which is a Gaussian PDF, is equivalent to minimizing the square in its exponent. Now for the several measurement, assume this equation again, where omega j are independent, identical, distributed, normal, zero mean, and common variance. The likelihood as in equation number 3. This is likelihood of the function x, as we seen before, that ML and LS estimate coincide, and therefore it is easily shown that they are given by the following expression, like this one. Both are equal, both are same. Because when we talk about the maximum likelihood for the sufficient statistic, this equals to this thing, and for the sufficient statistic, the maximum likelihood of x is equal to the z of mean of z. So as we seen before, the ML and LS coincide, and therefore the equation of this one is equal to this one. So the value of maximum likelihood is for the value LS. So both have same value, the mean as z. Okay, we just seen that your maximum likelihood estimator for the sufficient statistic is equals to this thing. So if both are same, then your least square estimator is equal to the mean of the z. So we can say that the z of mean is sufficient for finding the least square estimator, and also similarly z mean of z is sufficient to find the ML Estimator. So this estimate is known as the sample mean or sample average, since it estimates the unknown mean x of the k random variable from the line. Clear? So both are same, and both use this value to find the estimator. Now when we compare the MMSE and MAP estimator, so let's say in the single measurement example with a period PDF on the parameter to be estimated. This is discussed in the previous lecture. And the MLE and MAP estimator, the posterior PDF of X was obtained as this one. This is already obtained. We have discussed this thing where we solve the exponent power and we come across that epsilon z having some value. Okay, we solve for the epsilon z. So it is apparent that the mean of this quotient PDF is this thing. This is the mean value of this quotient PDF is the epsilon of z, which is also peak of this PDF. Thus, your estimator is having the expected value of x and condition of z equals to this one, and which is equals to this one. And how it is true, as we have seen before. As we have seen before that the MMSC which has an expected value of conditional probability, this one is with respect to the conditional PDF. This is same as this includes the bias formula. This is posterior PDF is included the bias formula. Okay. So the solution of this one is same as the MAP estimator, where we already solved the conditional probability of x, condition of z. Okay, we have already solved the p of x, condition of z in the MAP estimator like this one. So we can use the same thing in the MMSC estimator. Yeah. So if this is it, then we have already solved that the MAP estimator is equals to this one, and MMS estimator include this formula as well. So we can say that this value is equals to the expected value of the z. That is the MMSE estimator. The conditional mean coincide with the MAP estimator, which is also a conditional mean. Both are conditional mean. It means both have same mean, conditional p of x and p of x, condition of z. So in view of above equation number 13 and equation number 12 can also be written as this one. And in view of this equation 12 can also be written as this one. The conditional probability of x having a quotient of with mean like this and variance is equals to this one. So both are same. Why? Because in both estimator include the conditional mean p of x and z. P of x, condition of z, is used in the MAP estimator, and also it is used in the MMSE estimator. Okay. So what is the difference between the LS and the maximum likelihood estimator? What is difference between the least square estimator and the maximum likelihood estimator?
Least scale method used about.
Why both are same? As we discussed that both are same. Like here. So here I want to ask that what is difference between the LS and MLE? Yeah, can you tell me? Okay, just tell me what is the MLE?
MLE.
Uh, what is maximum likelihood estimator?
We don't know entirely. So we calculate the likelihood. So
Yes, you are right. Yes, you are right. If we do not know P of x, then we just use the likelihood of the x and we use the maximum likelihood estimator. So how the least square and the maximum are equivalent? Yeah.
omega j 1000
Yes, yes. As we can see easily that this we considering these measurements here in this part, and when we use the likelihood function, because the least square and the maximum likelihood both uses the likelihood function. Why? Because least square do not know the P of x and maximum likelihood estimator do not know the P of x. Okay, in both cases they do not know the P of x, so they just use this likelihood value. Okay, P of x is unknown. So in this case, when we expand this thing like this one, so this is a Gaussian of z having this mean and variance. This has the same effect as previous one, because previous equation of the maximum likelihood estimator, which is also equal to the likelihood, the answer of the solution of this likelihood must be the same. So both are same. In previous case, there was only the maximum likelihood estimator was equals to the c e power exponent power this thing, and this equals to z minus x. Okay, and the maximum likelihood estimator there was written as z minus x. Okay, but here when we can apply the derivative and equal to 0, derivative of the logarithm of the likelihood, then it will equals to the z of mean of the z. So then in this case the both will be same. Like here, for a single measurement is also equal to z, and for the several measurement it's also equal to z. So z is same as the maximum likelihood estimator. Now these are quality measures for the estimator. Unbiased estimator, there are two cases: non-Bayesian case. Non-Bayesian case, in non-Bayesian, for a non-random parameter x, an estimator is said to be unbiased if this expected value of the estimator is equals to the true estimator, is a true value. It can be never overestimated, it can be never underestimated. It exactly the true. It is exactly the true value. When we solve the expected value of the estimator, if it is equals to the true value of the parameter x, then it is said to be unbiased. If it is difference, if there is some error, between the x naught and x, then this is the biased. So where expected value, where x naught is the true value of the parameter x, and zk is equal to the measurement like z1 and z2 up to zk. So the expectation in 1 is over the estimate of the x, which is random variable. So here x is random because our z is random. The observation of the sensor is of course random. So it was calculated based on the z. So if z is random, then x estimator is also random. But this is a non-random. This is the true value of x parameter is non-random. So the x estimator is a random variable. It is the function of the measurement z. This is z, and is taken with respect to the conditional PDF like this one. P of zk, condition of x equals to x naught. So in other words, the estimator is said to be unbiased estimator of x if expected value of estimator is equals to the x for every possible value of x. So if x is estimated value of x is not unbiased, then the difference is called the bias of this estimated value of x. Okay, for example, this is our parameter, so having a true value x, and this is PDF of x2 and this is PDF of x1. We are taking suppose two PDF, but the PDF of x2 is exactly same as x1. So this is the unbiased estimator. So x2 is unbiased estimator, but x1 is not unbiased estimator because it is not equal to this one. Here, if this PDF is same as this one, then it is the unbiased estimator. But here some difference. Our true value of parameter x is here, but the PDF of estimator x1 is here. There is a difference. So this is bias of x1, and this is the unbiased estimator. Similarly, this thing again, the PDF of x2 is unbiased estimator because it means the x value, and this is far away, this is going this way, so this is bias. The difference of this thing and here is a bias of x1. Now for the Bayesian case, So when we talk about the Bayesian case, we use the Bayes formula, and we know the PDF of P of x. So if x is random variable, so Bayesian case use the x as a random variable, and non-Bayesian case use x as a non-random variable. Then the unbiasedness property of Bayesian case is written as this one: expected value of the estimator is equals to the expected value of the x. Where the expression on the left hand side, this one is with respect to the joint PDF, like this one, and the one on the right hand side is with respect to the P of x. This is expression is taken over P of x with respect to the P of x, because here we know the P of x, and in the previous case there was written x, because we do not know the P of x. In this case, the right hand side is with respect to the P of x. Now the above unbiased requirement requires that the estimation error, this one, by zero mean, that is mean of error is 0. Expected value of the mean is 0. So above equation 4b covers both cases. It covers both the Bayesian and non-Bayesian cases. So an estimator is unbiased if 4b holds for all values of k. Unbiased of ML and MAP. Now we want to show that these estimators are unbiased or biased. So as we know that the maximum likelihood is equals to this one, and MAP estimator is equals to epsilon of z, which is equals to this function. This is from previous lecture. Now here we want to show that both estimators are unbiased. Consider the ML estimate of the parameter x with a true value x naught. So here we do not know P of x. So here it comes that the maximum likelihood estimator is equal to z. From a single measurement like z equals to x plus w, its mean this one, expected value of the estimator equals to this one, and this z equals to x naught plus w. Okay, for the single measurement, x naught plus w, and x naught as a true value remains the same. Okay, because we do not know the P of x, this remains the same, plus E of w, and E of w is 0 because it's a 0 mean Gaussian, so it becomes 0. So expected value of the estimator is equal to x naught. So this means this is unbiased. This means that this is unbiased. Okay, we apply the expected value on both sides. Here z is a single measurement, x plus w. Now expected value of x naught remains the same, x naught, and expected value of omega is 0. So since the mean of Gaussian value is 0, okay. Now here we prove for the MAP estimator of x model as Gaussian random variable with the period, mean, and the variance, and independent of x, that is this one. And now apply the expectation on both sides. So here this is the same. We applied expected over the z. Okay. So now if we solve z equals to this thing x plus w, the x bar plus E of w. So E of w, expected value of w is 0, and this will equals to the same. And when we solve this, like we take a common factor, we just both are common, we take just common factor and solve this thing, then it will be equals to the x bar. here it is ignored because it is equal to 0, and when we solve this, taking the common factor as the numerator, as the denominator, and solve for the numerator, then it will comes like x bar. So both of these estimates are unbiased. I know the biased estimator. Are you all clear? Or shall we stop here and we can cover the few more slides in the next class? Because I think that you are not understanding.
That's better.
Hmm?
I think so.
I think totally we more check. Maybe we understand about all things, but now confused about it.
Ah.
Okay.
So we can cover this thing, or we can repeat this thing in the next class, but you have to study about these estimator,
Yes.
like maximum likelihood estimator, MAP estimator, and least square estimator, and minimum MMSE estimator. Why the maximum likelihood estimator is same as LS estimator, and why the MAP estimator is same as the MMSE estimator. Okay, so because these are the basic for study about the estimators, and so you have to understand, and you can open your book and go through the internet and try to understand, and then in the next class we can discuss again in this class. Okay, so rest part is nothing but just the measuring part, just like bias estimator and consistency and efficiency estimator and this thing. Okay, so we can cover few slides in the next class.
I need PPT 3 week on Blackboard.
Okay,
Not in here.
okay, just the lecture.
Last lecture. Blackboard.
Take now I will take your your room,
Office.
your office.
Ah.
Now